Hello students, today we're going to talk about the autonomic nervous system, chapter 15 in our book. We're going to go over some of the structural features, compare it with the somatic nervous system, and go over some of the physiological responses controlled by the autonomic nervous system. So the somatic nervous system is the system that receives information, sensory information about pain, temperature, basically what you could feel, something called proprioception, which is our brain understanding what we're doing, if we're moving, if our arms are moving and whatnot, and all the other senses, sight, hearing, taste, smell, all of that in your equilibrium. The effector for the somatic nervous system is skeletal muscles. So any reflex that involves skeletal muscle contraction is referred to as a somatic nervous system reflex. The autonomic nervous system receives sensory information from the organs in the body or any effector that we can't control consciously. Like the smooth muscle around blood vessels, around your stomach, around your intestine. I know I put muscle there, but that would be smooth muscle, or cardiac muscle, like in your heart, and the nervous system. So the autonomic nervous system is actually involved with regulating reflexes to control physiology of unconsciously perceived sensory input. And we're going to talk about some of that. So, the somatic nervous system structurally is set up different from the autonomic nervous system. And so what we're looking at with this picture right here, with the cross section of the spinal cord, the posterior root and anterior root of a spinal nerve, the somatic nervous system motor output has one motor neuron with the neuron cell body embedded in the anterior gray horn of the spinal cord. If it's leaving the spinal cord, going out straight to the effector, which is skeletal muscle. So there's only one neuron before it reaches its effector. That's different for the autonomic nervous system motor output. Also, all of these motor neurons that are part of the somatic nervous system are myelinated. That's what these little sausage-looking structures are around the axon. And all of those neurons that innervate skeletal muscle releases acetylcholine as its neurotransmitter. So acetylcholine is excitatory on skeletal muscle. But we're going to look in this chapter at the autonomic nervous system. Acetylcholine is not always excitatory. It depends on what type of receptor the effectors have. So, the somatic nervous system has one motor neuron that leaves the central nervous system and goes straight to its effector, which is skeletal muscle, and the neurotransmitter from that neuron is always acetylcholine. The autonomic nervous system is different structurally. The motor output from the autonomic nervous system involves two neurons that occur in series. They communicate with each other before the effector receives the signal. So the first neuron that leaves the central nervous system is referred to as the preganglionic neuron. The preganglionic neuron always has its cell body embedded in the central nervous system somewhere, and we're going to look at where that is. The postganglionic neuron is housed in the peripheral nervous system altogether. So the preganglionic neuron is always myelinated, and its neuron cell body is always embedded either in the lateral gray horn in certain regions of the spinal cord or in the nuclei of 4 cranial nerves, and we're going to look at what those are. The postganglionic neuron is always unmyelinated, and it has its cell body embedded in a peripheral ganglion somewhere, and then its axon then goes to the effector. So you could review this little animation, as are the other ones in all the other PowerPoints. So on this graphic, we can see the examples of the two major motor outputs of the autonomic nervous system, something called the sympathetic and something called the parasympathetic motor output. So the sympathetic motor output occurs in two ways. First, both motor outputs are going to have a preganglionic neuron, which is the first neuron in succession. Its neuron has its cell body always embedded somewhere in the central nervous system. If the preganglionic neuron has its cell body embedded in the spinal cord in different regions, its cell body is always embedded in the lateral gray horn of the spinal cord. So what we're looking at here is a preganglionic neuron leaving the spinal cord via the anterior root of the spinal nerve, and then going through the spinal nerve and terminating in something called the ganglion. A ganglion is a collection of neuron cell bodies in the peripheral nervous system. The neuron cell bodies that are in the ganglion, if it's an autonomic ganglion, is the cell body of the postganglionic neuron. So here's the preganglionic neuron. It's the neuron that occurs before the ganglion, and here's the postganglionic neuron. It occurs after the ganglion. The preganglionic neuron and the postganglionic neuron always make a synapse inside the ganglion, so that when the preganglionic neuron fires an action potential, it will dump out its neurotransmitters in a synaptic cleft, and then the postganglionic neuron will send an action potential down its axon away from the ganglion to go to the effectors in the body. The autonomic nervous system effectors are the organs and tissues in the body that we can't control consciously. So that includes some glands, the heart, smooth muscle. Those are effectors of the autonomic nervous system. And we're going to talk about adipose tissue as well. But nonetheless, the majority of the cases occur this way, where the preganglionic neuron dumps out acetylcholine as its neurotransmitter at the ganglion, and acetylcholine then binds to its receptor on the dendrites and cell body of the postganglionic neuron. And in this case, acetylcholine is excitatory, so we're going to talk about that as well, which causes the postganglionic neuron to fire an action potential. And when that action potential reaches the end of that postganglionic neuron, it releases norepinephrine as its neurotransmitter, which can be either excitatory or inhibitory on the effectors. It will either increase or decrease the metabolic activity of its effectors. So it's something that we have to talk about in this chapter. Now, there is one exception to the rule, where we have a preganglionic neuron and then a postganglionic neuron before we ever get to the effector to bring about a physiological change. And that exception is in the sympathetic nervous system, where a preganglionic neuron leaves the spinal cord via the anterior root of a spinal nerve and terminates in the very middle of the adrenal gland. So the adrenal glands lie on top of our kidneys. There are two major parts to it. There's an adrenal cortex on the outer part of the gland and the adrenal medulla in the middle. The adrenal medulla in the middle contains cells called chromaffin cells, right here. And when they receive acetylcholine from the preganglionic neuron in the sympathetic nervous system, the chromaffin cells then release epinephrine and norepinephrine into the blood. So ultimately, when we have a sympathetic reflex, often referred to as a fight or flight response, it involves both the nervous system controlled reflexes as well as hormonal or endocrine reflexes, because the sympathetic nervous system causes the adrenal gland to release epinephrine and norepinephrine into the blood. The parasympathetic nervous system always contains a preganglionic neuron that leaves via the anterior root of a spinal nerve if it's in the spinal cord. In this case, that's the picture they're showing. Or sometimes the parasympathetic system, the parasympathetic system has some of its preganglionic neurons leaving from the brain in four cranial nerves, and I'll show you that in a second. So that preganglionic neuron then leaves and terminates in what we call a parasympathetic ganglion. And there, the preganglionic neuron is going to release acetylcholine as its neurotransmitter. It's going to activate the postganglionic neuron to fire off an action potential, and the neurotransmitter released by the postganglionic neuron of the parasympathetic system is always acetylcholine. So let's talk about some of these things. These are the structural layouts for the sympathetic system and then the parasympathetic system. There are going to be some questions on where are the cell bodies located for the preganglionic neuron? Where are the cell bodies for the postganglionic neuron located? Well, the pictures show me exactly the layout. We'll show you also the exact layout of where the cell bodies are located and thus where communication will occur. So the ganglia always lie on the outside of the central nervous system, out in the periphery somewhere. And when it's a parasympathetic preganglionic neuron communicating with a postganglionic parasympathetic neuron, that ganglion is referred to as a parasympathetic ganglion. When it's a preganglionic neuron in the sympathetic nervous system communicating with the postganglionic neuron in the sympathetic nervous system, that ganglion is referred to as a sympathetic ganglion. And we're going to learn what those names are. So the autonomic nervous system is divided into both sympathetic and parasympathetic nervous systems. The sympathetic nervous system is also referred to the fight or flight division or the thoracolumbar division, ultimately because the sympathetic nervous system is the system that is activated in order to keep us safe when we're under stress or in an emergency situation. And so we're going to talk about what a fight or flight response is. The parasympathetic nervous system is referred to as the rest and digest division or the craniosacral division. And the parasympathetic nervous system is the nervous system that basically allows you to digest your food, gain energy, basically restore energy in the body. So I put in here a table. I want you to review this. We're going to talk about the stuff that is in this table just for the comparison of the somatic nervous system and the autonomic nervous system in general. Some of the different features, what's the sensory inputs, what controls the motor output, what are the motor neuron pathways. So for instance, in the somatic nervous system, we have one neuron, leaves the central nervous system and goes to the effector, which is skeletal muscle. In the autonomic nervous system, there are usually two neurons in succession before we get to the effector. There is an exception to that, and that deals with the adrenal medulla that is in this picture. This is the only exception to the fact that we normally have two neurons in succession. This one we only have one, and that's a part of the sympathetic nervous system. So just review the comparisons here for each one of these categories for the somatic and the autonomic nervous system. Now, the preganglionic neuron, again, in both the sympathetic and the parasympathetic nervous system, has its cell body embedded in the central nervous system. It's either going to be embedded in the brain, where they're in four cranial nerves, or somewhere in the spinal cord. The postganglionic neuron has its cell body always embedded in an autonomic ganglion, which exist out in the peripheral nervous system. The sympathetic division, or sympathetic nervous system, is called the thoracolumbar division because all of the preganglionic neuron cell bodies in the sympathetic nervous system are located in the lateral gray horns from the thoracic to the lumbar region of the spinal cord. I'll say that again. The preganglionic neuron cell bodies in the sympathetic nervous system always have their cell body embedded in the lateral gray horn of the thoracic to the lumbar region of the spinal cord. So all of the sympathetic output from the central nervous system comes from the thoracic and the lumbar region of the spinal cord only. So let's look at a picture that demonstrates that. This picture has a lot of information on it, and it can really tell you a lot about the sympathetic nervous system if you know what you're looking at. So let me show you first off. From T1 down to L2 or L3, in that region, the first few in the lumbar region, the thoracic to the lumbar region of the spinal cord is where all of the cell bodies, which are those little bitty dots, of the preganglionic neurons are located for the sympathetic nervous system. So all of these neurons that are leaving the spinal cord from the thoracic to the lumbar region are the preganglionic neurons of the sympathetic nervous system. These have nothing to do with the parasympathetic system. Also, something else that you can notice from the picture, these neurons, the first neuron, the preganglionics, the artist drew a solid line. That solid line means that all of those preganglionic neurons are myelinated. But then if you look over here, you have all these dotted blue lines that go to the different organs and tissues in the body. The dotted lines are the postganglionic neurons, and the dotted line represents the fact that the postganglionic neurons are always unmyelinated. So the way that this works is this: when the sympathetic nervous system fires, or sends action potentials, which we're going to cover, the action potential leaves via the preganglionic neuron from the thoracic to the lumbar region of the spinal cord, and then that preganglionic neuron is going to make a synapse out in the periphery of the body somewhere with the cell body and dendrites of the postganglionic neuron. So what you're looking at right here on either side of the spinal cord, this represents a sympathetic chain ganglion. It's called the sympathetic trunk or chain ganglia. Ganglia, plural, ganglion, singular. So the only neurons that communicate or synapse in the sympathetic chain are preganglionic sympathetic neurons and postganglionic sympathetic neurons. There are other ganglia, though, that lie on the outside of the chain. They lie out near large arteries in the body, and I'm going to give you those names in a minute, and that's what some of these other circles are that you see here. So these are called prevertebral ganglia, or collateral ganglia was an older name for them, and they have specific names. This one is the inferior mesenteric ganglion. So you can see here that the preganglionic neuron comes out, it bypasses the chain ganglion, but then makes a synapse in this ganglion with the postganglionic neuron. So there are two main types of ganglion for the sympathetic nervous system, and I'm going to give you those names in a minute. So when the preganglionic neuron fires, it synapses in a ganglion somewhere, sympathetic ganglion somewhere in the periphery, and then causes the postganglionic neuron to fire, which dumps out neurotransmitters on its effector. Now, depending on what type of receptor the effector contains, the organ can increase or decrease its metabolism. I'll give you an easy one right now. So if the sympathetic nervous system fires to our heart, so you see your heart over here, The preganglionic neuron is going to fire. It's going to synapse with a postganglionic neuron that then goes to the heart. And the sympathetic nervous system, when it fires, increases our heart rate. That's why when you're running on a treadmill, your sympathetic nervous system is firing because you're active and your heart rate goes up. Also, the force of contraction goes up, which helps increase blood flow and blood pressure in the body. But nonetheless, the point is that the sympathetic nervous system, when it fires to the heart, it causes cardiac function to increase. So the heart rate goes up and the force of contraction goes up, so the heart pumps more blood out per minute, which is called cardiac output. But nonetheless, you can see where the cell bodies are located for the preganglionic neurons, always in the thoracic to the lumbar region, and the postganglionic neuron cell bodies are always out in the periphery in a ganglion somewhere, and before the axons go to their targets or their effectors. The parasympathetic nervous system has its preganglionic neuron cell bodies either embedded in the brain in 4 cranial nerves. The oculomotor, cranial nerve number 3, you just covered in chapter 14. The facial, which is cranial nerve number 7. The glossopharyngeal nerve, cranial nerve number 9. And the vagus nerve, cranial nerve number 10. So here's cranial nerve number 3, number 7, number 9, and number 10. So the nuclei in the brainstem contains preganglionic neuron cell bodies of the parasympathetic nervous system. So some preganglionic neurons from the parasympathetic nervous system leave the brain in those 4 cranial nerves. That would be the motor output for some of the parasympathetic division. However, there are some parasympathetic preganglionic neurons that have their cell body embedded in the sacral region of the spinal cord, in the lateral gray horn of the sacral region of the spinal cord. So since the preganglionic neurons are either leaving the brain in 4 cranial nerves or leaving the sacral region of the spinal cord, the parasympathetic division is also called the craniosacral division or outflow, and that's why they call it that. So let's look at the picture. So here's the picture. Here's the preganglionic neurons. You see their cell bodies up here, embedded in the nuclei of those 4 cranial nerves that was just mentioned, off of the brainstem. But some of the preganglionic neurons of the parasympathetic system have their cell body embedded in the lateral gray horn of the sacral region of the spinal cord. So for that reason, the parasympathetic nervous system is referred to as the craniosacral division, because its preganglionic neurons only ever leave from the brain or from the sacral region of the spinal cord. So the picture definitely shows me that. The other thing I can see again is that some of these red lines are solid, but some of them are dotted. So these solid red lines are the myelinated axons of the preganglionic neuron. The dotted red lines are the unmyelinated postganglionic neurons. And one other thing that we can notice from this picture to the last one, which I'll pull back up, is that the preganglionic neurons in the parasympathetic nervous system are typically much longer and then have very short postganglionic neurons. So notice on this one, the preganglionic neuron is very long, but that little bitty neuron right there or here or there, those are the postganglionic neurons, which are typically quite short, because the synapse of the parasympathetic preganglionic neuron with the parasympathetic postganglionic neuron are at what's called a terminal ganglion. The preganglionic neuron pretty much terminates at the organ of interest. Notice at the heart, the preganglionic neuron comes in and then is terminating there, and the postganglionic neuron is lying right on or next to the organ of interest, in this case the heart. So let's go back to the sympathetic system for a second. Typically in the sympathetic system, the preganglionic neurons are shorter and the postganglionic neurons are longer. So the preganglionic neurons in both divisions, sympathetic and parasympathetic, are myelinated. In the sympathetic system, the preganglionic neuron typically is shorter, and the postganglionic neurons in both systems are always unmyelinated. And in the sympathetic system, the postganglionic neuron is typically much longer. So here we can see that the preganglionic neurons are going to leave either from the brain in these 4 cranial nerves that I just mentioned, the oculomotor, the facial, glossopharyngeal, and the vagus nerve, or from the sacral region of the spinal cord and go to their effectors. Now, notice here, we have red lines going to each tissue and organ in the body. For instance, the heart. Let's focus on that again. So you have a parasympathetic innervation to the heart, and if I go back, there is a sympathetic innervation to the heart. So typically, the organs, effectors, and tissues in the body have what's called a dual innervation. They receive both a sympathetic postganglionic neuron and a parasympathetic postganglionic neuron. So what that is all about is this. The sympathetic and the parasympathetic nervous systems are innervating the same tissues. There are some that don't get parasympathetic, but the tissues that do get both sympathetic and parasympathetic, when one of the system fires, it turns the organ on, and when the other system fires, it turns the organ off. It's not always just on and off, but we can say it increases and or decreases the metabolism of the effector or the organ. For instance, when you are resting, your parasympathetic nervous system is firing more than the sympathetic system. And so everybody knows when you're resting, you have something called your low resting heart rate. I'm sure you heard of that before. The reason why your heart rate is lower when you're resting relative to if you're physically active is because the parasympathetic nervous system is firing to your heart. And the neurotransmitter that is released by these postganglionic neurons is acetylcholine. So although acetylcholine is excitatory on skeletal muscle and makes it contract, acetylcholine is inhibitory on the heart. So when the parasympathetic nervous system fires, the heart rate is going to go down. On the other hand, if you're getting up and you're going to the gym and you start moving and you're working out, the sympathetic nervous system fires more often when we are either in an emergency situation or we're physically active. So the sympathetic nervous system fires going to the heart for this example, and it dumps out norepinephrine as its neurotransmitter, and norepinephrine on the heart increases your heart rate, and it increases the force of contraction so the heart can pump more blood to the muscles in the body that are working out. They need more blood flow to them. So the sympathetic nervous system increases cardiac function, whereas the parasympathetic nervous system decreases cardiac function. So that's what we call a dual innervation. Now there are some tissues that only receive sympathetic stimulation, or I should say innervation, and not parasympathetic. And I'm going to mention some of those in a minute. But before we do that, let me talk about the ganglion and what their names are. We're going to have a couple of questions on the names of the ganglia and what is synapsing in the ganglia. So, in the body, we always have 2 different types of autonomic ganglia, sympathetic and or parasympathetic ganglia. We'll do the parasympathetic ganglion first. Parasympathetic ganglia are called terminal ganglia because the preganglionic neuron of the parasympathetic nervous system terminates at the organ of interest. So let's go back to the picture. Look over here for the heart again that we were just talking about. The preganglionic neuron comes in and is going it goes all the way to the organ, the effector. before it ever makes a synapse with the postganglionic neuron. So for that reason, we call the ganglion where a parasympathetic preganglionic synapses with a parasympathetic postganglionic neuron, we call that ganglion a terminal ganglion, because the preganglionic neuron is terminating at the organ of interest and then making a synapse with the postganglionic neuron. Now, the sympathetic ganglion come in two types. I mentioned these already, the sympathetic trunk or chain ganglion, you might see that name, sympathetic trunk or the sympathetic chain ganglia plural. These are a pair of ganglia that lie in a vertical row up and down our vertebral column, just lateral to the spinal cord. So let me go back to the picture of the sympathetic nervous system. Here is the sympathetic chain ganglion, right here. All of these little nodules that you see that the artist drew in is where sympathetic pre- and postganglionic neurons can communicate. And that's what a ganglion is. It's where a pre- and a postganglionic neuron is communicating, at least in the autonomic nervous system. So a ganglion, by definition, is a collection of neuron cell bodies out in the peripheral nervous system somewhere. And since only sympathetic pre- and postganglionic neurons are communicating or synapsing in this ganglion, this would be called a sympathetic ganglion. So this particular ganglion, which is called the sympathetic trunk or chain ganglia, is where sympathetic pre- and postganglionic neurons communicate or make a synapse. The other types, the other types of sympathetic ganglia, which lie on the outside of the trunk, more towards the anterior side of the body, typically by large arteries, those are called prevertebral ganglia or collaterals. So the prevertebral ganglia occur in three forms that I want you, well, the three main ones I want you to learn. There's typically 5 or so, but we're going to learn these 3 main ones. We're going to cover these arteries in AMP2 as well. So we have what is called a celiac ganglion, a superior mesenteric ganglion, and an inferior mesenteric ganglion. So these ganglia are part of the sympathetic nervous system. They take on the name of celiac or superior and inferior mesenteric because the ganglion lies next to those arteries. So there's a big artery comes off the aorta called the celiac artery, really the trunk. There's a superior and an inferior mesenteric artery. So the ganglia that lies there takes on the same name. The only neurons that synapse in the celiac, superior, and inferior mesenteric ganglia are sympathetic pre- and post-ganglionic neurons. The only neurons that communicate or synapse in a terminal ganglion are parasympathetic pre- and post-ganglionic neurons. Now, as far as the synapse is concerned, dealing with the sympathetic pathway, there are 4 ways that the sympathetic preganglionic neuron can synapse with the postganglionic neuron. So I'm going to show you these 4 ways off of this next picture. So just read through that and then review it on this picture. So let me tell you what we're looking at here. First of all, we're looking at a section through the spinal cord. The preganglionic neuron is going to leave somewhere from the thoracic to the lumbar region of the spinal cord, since it's the sympathetic nervous system, via the anterior root of a spinal nerve. Now, the axon of that preganglionic neuron is going to enter the spinal nerve. There is a connection between the spinal nerve and the sympathetic chain ganglion. There's 2 little connectors. The 2 little branches that connect the spinal nerve to the chain ganglion are called the rami communicantes. Rami communicantes. There are 2 rami communicantes. And a ramus, by the way, is just a branch. It's called communicantes because it communicates from the spinal nerve to the chain ganglion. So the two branches are these. This more lateral branch that we see here, which carries the preganglionic neuron in, and here it comes. That solid line means it's myelinated. This branch of the rami communicantes is called the white ramus. So you see that name here. The reason why it's called the white ramus is because it only carries myelinated neurons, and that myelination appears a glistening white. So that preganglionic neuron can come in and join the sympathetic chain ganglion via the white ramus. Now here are your choices. That can happen. That preganglionic neuron can synapse with a postganglionic neuron at the same level that the preganglionic neuron comes in. Just like this, at this level of the spinal cord. And then the postganglionic neuron can leave at that same level via this branch, which is called the gray ramus. It's called the gray ramus because the postganglionic neuron is unmyelinated and it's going to rejoin the spinal nerve. So we have a white ramus and a gray ramus. The white ramus carries the sympathetic preganglionic neuron into the chain ganglion, and the gray ramus carries the unmyelinated postganglionic neuron back out. Now, that preganglionic neuron, though, can have branches that can go up or down the length of the sympathetic chain ganglion, up and down the spinal cord, and can synapse with other postganglionic neurons at different levels up and down the spinal cord. In that way, we can have a broader postganglionic neuron output, motor output, to multiple effectors around the body at the same time, which brings about the sympathetic reflex, as we call the fight or flight response. So the second option for that preganglionic neuron is it can go up or down the sympathetic chain ganglion and synapse with a postganglionic neuron at a different level than where it entered the chain ganglion. Now, we can also have that preganglionic neuron leave the sympathetic chain. Typically occurs down at the splanchnic nerves and can ultimately synapse in one of the prevertebral ganglia. So notice the preganglionic neuron comes in and then it leaves and goes to another ganglion out in the body. This would be called a prevertebral ganglion. That is either referred to as a celiac, the superior mesenteric, or the inferior mesenteric ganglion. The example they're showing on the picture for demonstration purposes is the celiac ganglion. And there we have a synapse with the preganglionic neuron with a postganglionic neuron that then goes out to its effector, in this case smooth muscle around the stomach. Excuse me. Then the last option that we have is for the preganglionic neuron that does not synapse with a postganglionic neuron. We have a preganglionic neuron that goes straight to the adrenal medulla. Here's the adrenal gland. These lie on top of our kidneys. The very middle of the adrenal gland is what produces adrenaline or epinephrine and noradrenaline or norepinephrine. And the cells that do that are called chromaffin cells. So we have a preganglionic sympathetic neuron that goes straight to the adrenal medulla, so that when we have a fight or flight response or a sympathetic response, we're innervating all of these different effectors and tissues up and down throughout the entire body, along with activating the release of epinephrine and norepinephrine from the adrenal medulla. So for that reason, a sympathetic reflex really involves the sympathetic nervous system and the endocrine system, since we're causing the release of hormones from the adrenal medulla. Now here's the parasympathetic motor output. You can see it's a little different. We have the preganglionic neuron leaves via the anterior root of a spinal nerve. This would only occur in the sacral region of the spinal cord, because if these neurons were leaving from the brain, they would not be leaving from a spinal nerve, from the spinal cord. They would be leaving through cranial nerves number 3, 7, 9, and 10, and in cranial nerves. But here we have the preganglionic neuron entering the spinal nerve via the anterior root of a spinal nerve that then goes all the way to its effector, smooth muscle in the urinary bladder in this example. And there it terminates and communicates or synapses with the postganglionic neuron. And for that reason, parasympathetic ganglia are called terminal ganglia. And the postganglionic neuron fires and then brings about its effect on its effector. All right, so please review this animation. It's just the organization and overview of the nervous system and really the autonomic nervous system that we're talking about. Now, we have to start getting into the physiology part of the autonomic nervous system, which is going to involve knowing what types of neurotransmitters are being released by which neurons and which types of neurotransmitter receptors that are going to bind to those neurotransmitters. So any neuron that releases acetylcholine as its neurotransmitter is referred to as a cholinergic neuron. So all neurons that release acetylcholine are cholinergic. All receptors that bind to acetylcholine in the body are called cholinergic receptors. There are two basic types of cholinergic receptors with subtypes in there, but two basic classes of them. One major class is called a nicotinic receptor, and the other major class is called a muscarinic receptor. I'm going to show you where they're located in a minute. But both of these types of receptors bind acetylcholine. They never bind epinephrine or norepinephrine. Adrenergic neurons are neurons that release norepinephrine as its neurotransmitter. And the receptors that bind to norepinephrine from the sympathetic system or from epinephrine and norepinephrine from the adrenal medulla are referred to as adrenergic receptors, which we have to look at what those types of receptors are. So here we have some pictures that demonstrate the pre and the postganglionic neurons in the sympathetic and the parasympathetic nervous system. We'll do the sympathetic system first. Here you see a preganglionic neuron. This cell body would always be embedded in the lateral gray horn of the thoracic to the lumbar region of the spinal cord. Its axon would leave in the anterior root of a spinal nerve and then go to the ganglion in the body somewhere. This sympathetic ganglion, this gray circle, will either be the sympathetic trunk or chain ganglion, or it will be a prevertebral ganglion. So let's notice some things right away off the picture. Number one, the preganglionic neurons are always myelinated. So that's what those little sausage looking things are. Every single preganglionic neuron, 100% of them without exception in both sympathetic and parasympathetic nervous systems release acetylcholine as its neurotransmitter. So that means all preganglionic neurons in both systems are cholinergic. Now, the postganglionic neurons in both systems, sympathetic and parasympathetic, always have receptors that can bind acetylcholine. And as it turns out, the receptors that are on the dendrites in the cell bodies of parasympathetic and sympathetic postganglionic neurons, those receptors are referred to as nicotinic receptors. Nicotinic receptors are always excitatory. Those nicotinic receptors are also the ones that are located on the motor end plate of skeletal muscle that you learned about in Chapter 10. And when the somatic nervous system motor neuron fires, releases acetylcholine at the neuromuscular junction, it caused the skeletal muscle to contract because the receptor on the skeletal muscle was excitatory. So that's the same thing here. These nicotinic receptors that are on the dendrites and cell bodies of these postganglionic neurons receive acetylcholine. So that when the preganglionic neuron fires, acetylcholine is released, It binds to the nicotinic receptors, which cause the postganglionic neuron to fire an action potential, and then they release their neurotransmitter. So the differences between the systems come in the form of the neurotransmitters that are being released by the postganglionic neurons, because they're different in both systems. So the majority of the sympathetic division has a postganglionic neuron that releases norepinephrine. There are slight exceptions to that, which I'll mention in a second. But I can say almost all postganglionic neurons in the sympathetic nervous system are adrenergic. In other words, they release norepinephrine as their neurotransmitter. The effectors that they are trying to either activate or inhibit always have receptors that can bind norepinephrine. And receptors that bind to norepinephrine are referred to as adrenergic receptors. Now, the majority of the cases for the sympathetic system is the picture that you see at the top. The preganglionic releases acetylcholine, binds to a nicotinic receptor on the cell body and the dendrites of the postganglionic neuron. The postganglionic neuron fires and releases norepinephrine onto its target, where the norepinephrine will bind to an adrenergic receptor. About 15% of the sympathetic postganglionic neurons release acetylcholine, though, and almost all of these that release acetylcholine are innervating sweat glands in the body. So the sweat glands in the body that are being innervated by the sympathetic nervous system, like the ones on the palms of your hands and the soles of your feet, those postganglionic neurons release acetylcholine onto the sweat gland, which makes them produce more perspiration when you're afraid or scared or you're going through a fight or flight response. And the receptor on the effector that binds acetylcholine is not a nicotinic receptor. They're referred to as a muscarinic receptor. There's different types of muscarinic receptors. Some of them are excitatory and some of them are inhibitory. We're not going to learn all the different subclasses of them, but some activate the effector and some inhibit the effector. So in this case, the preganglionic neuron releases acetylcholine, binds to nicotinic receptors on the dendrites in the cell body of the postganglionic neuron, which makes it fire off an action potential. It dumps out acetylcholine at its effector, and it binds to a muscarinic receptor. In this case, these muscarinic receptors are excitatory, and it makes us produce perspiration. Now, the parasympathetic nervous system is all just one thing. There's no exceptions like the two we see here. The parasympathetic nervous system, the preganglionic neuron is still all cholinergic, just like all of them. They release acetylcholine on the dendrites in the cell body of the postganglionic neuron. And the postganglionic neuron, every single one of them in the parasympathetic nervous system are cholinergic. They always release acetylcholine. And so acetylcholine is going to bind to a muscarinic receptor on its effector cell or organ. So nicotinic receptors and muscarinic receptors bind acetylcholine only. Nicotinic receptors are found in autonomic ganglia, where we have synapses between pre- and postganglionic neurons. Muscarinic receptors are always found on the effector that is going to either be activated or inhibited. It depends on the exact type of receptor. For instance, the muscarinic receptor on your heart, when the parasympathetic nervous system fires, it slows your heart rate down. That's because the muscarinic receptor on the heart causes the heart to decrease its function. Ultimately, because it's a ligand-gated potassium channel is the receptor, if you wanted to go look that up. But it causes the pacemaker of the heart to be hyperpolarized, and thus prevents it from firing an action potential, and it slows your heart rate down. But nonetheless, the muscarinic receptors are either excitatory or inhibitory. It depends on the effector that is being innervated. The adrenergic receptors come in two major forms. They're referred to as alpha adrenergic receptors or beta adrenergic receptors. So down here I shortened it up and said alpha and beta. So alpha adrenergic receptors or beta adrenergic receptors always bind norepinephrine. They can also bind epinephrine as well, that's being released by the adrenal medulla. But talking about the sympathetic nervous system right now, the alpha and beta receptors are located on the effectors, not on the neurons. So the effectors out in the body either will have muscarinic receptors or alpha and beta adrenergic receptors. So, or both. They have, many tissues contain both because they're being dually innervated by both systems. So instead of making us memorize exactly the receptor distribution around the body, I came up with some generalities to help us learn a little bit about these receptors. First of all, there are different subclasses of the alpha and beta receptors. There's alpha 1s and alpha 2s, beta 1s, beta 2s. There's also a beta 3. So alpha 1 and beta 1 receptors typically are excitatory. That means that if an effector has an alpha 1 or a beta 1 receptor, when the sympathetic nervous system fires, it's going to increase the metabolism of that particular effector. On the other hand, some effectors have alpha 2s and beta 2s, and these are typically inhibitory. So if the effector out in the body had alpha 2s or beta 2 receptors, that particular effector would be inhibited. Beta 3 receptors are only found on brown fat or brown adipose tissue, and so when the sympathetic nervous system fires, it basically causes the brown fat to burn lipids aerobically, and it produces heat as a byproduct. So that's called thermogenesis. And babies and young children, which still have a lot of brown fat nodules, utilize this system to increase their body temperature, because babies can't regulate their body temperature very well when they're first born. Most adults have very little brown fat left, so we don't rely on that to maintain our body temperature. Now, I also want us to learn the enzymes that break down norepinephrine. And if you forgot that from chapter 12, I need you to relearn it. So there are enzymes that remove the neurotransmitters from the clefts. There's one called monoamine oxidase, or MAO, or catecholomethyltransferase, or COMT. These two enzymes break down norepinephrine and thus renders it non-functional, and it stops the reflex, the sympathetic reflex. Now let's go through the fight or flight response. The fight or flight response occurs when you're nervous or scared or something like that, or very excited. So your sympathetic nervous system is turned on, and it starts to fire and override the parasympathetic nervous system during what we refer to as the E situations. When you're in an emergency, your sympathetic nervous system is going to fire. When you're embarrassed, like if you have to get up in front of a class and give a speech and it kind of makes you nervous, you kind of get butterflies in the stomach and your hands get cold and clammy and basically nervous. That's a mild fight or flight response. So that happens when you're embarrassed, or when you're very excited, or when you're exercising. This is when the sympathetic nervous system fires. And our sympathetic nervous system makes us use energy. That's our energy system predominantly. So when you're very scared or in an emergency situation, you go through an alarm reaction, which is referred to as a fight or flight. That means you'll either run as fast as you can, flight, get away from the situation, or you'll fight as hard as you can to survive. So some tissues in the body have to increase what they're doing, and other tissues have to decrease what they're doing in order for all of the energy to be focused on those essential organs to help keep you living if you're in a very, very bad situation. Like if someone is trying to hurt you or whatnot, you have to focus all of that energy in your body to the essential organs, which I need to talk about some of those. So when you go through a fight or flight response, your pupils will dilate. These are sympathetic nervous system outcomes, responses. Your pupils dilate, that allows a maximal amount of light to enter your eye so you can see what's going on better. Your heart rate and the force of contraction and your blood pressure, that's what BP is, all increase. Your sympathetic nervous system increases cardiac function. Let's face it, if you need to run or fight as hard as you can, you're going to have to be using your muscles, and they're going to need a lot of blood flow, so your heart's going to have to pump more blood to the essential organs. So let's talk about that. During a fight or flight response, if you need to send more blood to the essential organs, then that means you have to take blood away from an organ because you only have a set volume of blood in the body. So we actually decrease blood flow to the non-essential organs, and I listed a few of them out, or systems really. If you are, let's say you're running down a dark alley, someone's trying to hurt you or, God forbid, kill you, then you don't have to digest a hamburger that you might have eaten for lunch. So the digestive system organs are non-essential at that moment. You don't need them to live if you're about to die immediately. Your reproductive structures and organs, they're non-essential. Your kidneys and other parts of the renal system are not all that important at that moment. Obviously, everything in our body is important, but not at that moment. So we have to decrease blood flow to these types of organs and tissues. So how do we do that? Well, you do that through vasoconstriction and vasodilation. Vasoconstriction is when the diameter of a blood vessel decreases. Vasodilation is when the diameter of a blood vessel increases. So if you want to decrease blood flow to a tissue, you can constrict the blood vessels off at that tissue. And if you want to increase blood flow to a tissue, you can dilate the blood vessel so more blood volume can get through the blood vessel. So how do we constrict or dilate the blood vessel then? Well, there is smooth muscle around the blood vessels in the body. And if the sympathetic nervous system fires and the tissue's blood vessel smooth muscle has alpha 1 or beta 1 receptors, typically alpha 1s, then, which are excitatory, the smooth muscle will contract and it clamps the blood vessel off. If the tissues have alpha 2s or beta 2 receptors, which are typically inhibitory, mainly beta 2s for the smooth muscle, then the smooth muscle relaxes and the blood vessel dilates. So, without memorizing where alpha 1s and beta 2s are located and whatnot, we can infer something here. The non-essential organs need to have blood taken away from them. We need to decrease blood flow to them so we can send that blood to the essential organs. So all of the tissues and organs in your digestive system, reproductive system, and renal system have alpha 1s and beta 1s, the blood vessels, so that when the sympathetic nervous system fires, those blood vessels constrict. Brings about vasoconstriction, which decreases blood flow to them. The essential organs in our body include, well, I didn't write all of them down, but skeletal muscle, cardiac muscle, your liver, your brain, and your lungs. Let me tell you why. Your brain needs more blood flowing to it because you have to think very clearly. Your lungs need more blood flowing to it so they can oxygenate more of the blood because your muscles and your heart and other tissues are about to work a lot and they need more oxygen to make ATP. Your skeletal muscles are the ones that are contracting to either make you run or fight, so they need more blood going to them, so they're essential. And then the heart itself obviously is important because it's the effector that is pushing blood through the body. Now the reason why your liver is important is because your liver stores sugar. And during a fight or flight response, a sympathetic event, your blood sugar levels go up a little bit in your blood. And the reason for that is because the sympathetic nervous system activates the liver to release sugar into the blood, really via two things. We'll learn more of this later, but it's called glycogenolysis and gluconeogenesis. Those two events in the liver increase with the sympathetic response, which increases our blood sugar. So we need more blood sugar because the skeletal muscles are trying to use as much energy as possible so they can contract more efficiently. So these are what I would call the essential organs to keep you healthy in an emergency situation. Your brain, your lungs, skeletal muscle, cardiac muscle, and your liver. Now, a sympathetic response also causes bronchodilation. This is an increase in the diameter of your airway, so it's easier to breathe. So it increases the diameter of the airway, called bronchodilation, and your sympathetic nervous system increases your respiratory rate, so you can oxygenate the blood more efficiently. So, and I've already said that your blood glucose level will increase. That's mainly due from the liver. Not the only thing, but mainly from the liver. All right, so that's a sympathetic response. So make sure you review that. I think they have some pretty good tables in your book that I might have left out of this PowerPoint, but just review the responses for the fight or flight response. Now, let's talk about the parasympathetic system with its receptors. So the parasympathetic nervous system, again, is all cholinergic. The preganglionic neuron releases acetylcholine. The postganglionic neuron releases acetylcholine, and so they're both cholinergic. Nicotinic receptors are always found on the dendrites in the cell body of a postganglionic neuron only. Muscarinic receptors are always found on the effectors out in the body. So we have to know that distribution. Nicotinic receptors are found on the postganglionic neurons, but the muscarinic receptors are found on the effectors. Now, both the nicotinic receptors and the muscarinic receptors can bind acetylcholine. The reason why they're called nicotinic or muscarinic is this. Nicotinic receptors can also bind nicotine, so they're called nicotinic. Muscarinic receptors are called muscarinic because those receptors can bind to a mushroom poison called muscarine. And as it turns out, muscarinic receptors can bind to muscarine, but it can't bind nicotine. Nicotinic receptors can bind nicotine, but it can't bind to muscarine. But what's kind of interesting is that both of these receptors can bind to acetylcholine. And I won't go into details about why that is, but both of those receptors bind acetylcholine. The nicotinic receptor is also the type of receptor that's located at the neuromuscular junction. However, this is part of the somatic nervous system, not the autonomic nervous system, but that same type of receptor is excitatory on skeletal muscle, right? So let's go over the parasympathetic responses. Now, the parasympathetic nervous system, called the rest and digest system, is the part of the motor output of the autonomic nervous system that overrides most of the day. So most of the day, our parasympathetic nervous system is firing. Your sympathetic nervous system sporadically fires over the parasympathetic nervous system depending on what you're doing. If you're lying on a couch all day long and you're not moving, your parasympathetic nervous system is the one that's firing. But the minute you start to get up and walk around or become physically active, or if you get very nervous or you're in one of those emergency situations, the parasympathetic nervous system stops firing and the sympathetic nervous system fires to bring about the sympathetic reflex or fight or flight response. Now, let's go over the 5 major responses of the parasympathetic nervous system. Right? So the parasympathetic nervous system is going to be firing when we're resting. It allows us to digest our food, and it makes our body restore its energy, conserve and restore energy in our body. Now, the acronym SLUD stands for salivation, lacrimation, urination, digestion, and defecation. These are the 4 major activations or increases of the parasympathetic nervous system. For instance, when we get hungry, we start to salivate, produce saliva. You know, part of the digestive system reflexes that we'll learn later. But Nonetheless, we increase salivation with the parasympathetic nervous system. You increase tear production, tears. That's called lacrimation, if you've never heard of that. Lacrimation is the production of tears. So that increases with the parasympathetic nervous system. Urination, going to the bathroom, digesting your food, and defecation, going to the bathroom, all of those are activated by the parasympathetic nervous system. There are 3 important decreases that occurs because of the parasympathetic nervous system, though. When the parasympathetic nervous system fires, it decreases your heart rate. So that's why we have a low resting heart rate when we're resting, because a parasympathetic nervous system is dumping out acetylcholine onto our pacemaker, and the muscarinic receptor on the pacemaker is a ligand-gated potassium channel, which is inhibitory. So it inhibits the pacemaker and your heart rate goes down. The diameter of your airways go down. That's called bronchoconstriction. So our parasympathetic nervous system decreases some of the bronchial tubes a little bit through what we call bronchoconstriction. We also decrease the diameter of our pupil. So your pupil constricts down and gets smaller with parasympathetic output, but it actually dilates and gets bigger with sympathetic output. So those are the main reflexes of the parasympathetic nervous system that I want you to make sure you kind of understand. And the last thing I put down here is something called paradoxical fear. A paradoxical fear event is a fear event where someone thinks that they are definitely going to die. There's no escape from their stress or whatever they're going through if someone's trying to hurt them and whatnot. And so I don't know if you've ever seen, like in a movie, or heard that people lose control of their bowels when they get real nervous or real scared. That is a paradoxical fear event. So when they're very scared, the scaredest that they could ever be, which is subjective. What scares one person doesn't scare someone else. But nonetheless, something that is very fearful to somebody could cause a massive activation of the parasympathetic nervous system that then causes urination, because it activates urination, and defecation. So the people go to the bathroom on themselves when they are very frightened. Remember, normally when you're very scared, you're going through a fight or flight response, which is a sympathetic event. The sympathetic nervous system decreases digestive function, decreases renal function, all of that. So you're not going to go to the bathroom on yourself because of the sympathetic nervous system. You're going to go to the bathroom on yourself because of the parasympathetic nervous system firing. All right, so with that, I put in a table that compares the sympathetic nervous system, and you see thoracolumbar division, with the parasympathetic nervous system, or craniosacral division. So I want you to make sure you go through each one of these categories and compare the distinction between sympathetic and parasympathetic. So it's got some really good information in one place on this table, and that's why I put it in there. All right, so if you have any questions, just email me and I'll get back to you. Please review the video a few times before we talk about it. All right, thanks.